Hi everyone, this is Maverick Paul, the Chemistry Guru. Now in this video, we want to discuss the suggested solution for 2021 A-Levels H2 Chemistry, Paper 1, Question 4. So let's take a look at this exercise. Question 4, the 7th, 8th, 9th and 10th ionization energy of 4 consecutive elements in the periodic table, W, X, Y and Z are shown. So we have this information here. Later we will take a look at this in detail. So which element has the highest first ionization energy? Is it W, X, Y or Z? Now the topic tested in this exercise is still under atomic structure, and essentially what we want to do is we want to look out for a big jump in ionization energy, because a big jump in IE will correspond to a change in the principal quantum shell. So we actually learned this under successive IE. When we have a successive ionization energy, we know that as I progressively remove more and more electron, after the first electron, first IE, then the second IE, third IE, as I remove more and more electron, the ionization energy will always increase because the electrons are progressively getting closer and closer to the nucleus, and the attraction is stronger and stronger, so it requires more and more energy to remove. And when there's a change in the principal quantum shell, the electrons are much closer to the nucleus. Let's say, for example, if I switch from n equals to 3 to n equals to 2, and there's a very big jump in the distance from the nucleus, electrons are much closer to the nucleus, so the attraction is significantly greater, and therefore it requires a very big increase in the amount of energy for me to remove the electron. So usually when we do identification of unknown species using successive ionization energy, we always look out for big jump in IE because it is the most reliable. We don't care about the subshell, we don't care about a small jump, we always look out for the big jump in IE, and this will correspond to a change in principal quantum shell. What we want to do now is, I want to look at all this data and I want to deduce what is the group of one of these elements. Because the question already tells me that the elements are consecutive, I just need to identify one of these guys, which group one of these guys is in, then I can actually figure out the rest of the species. So some of the data is not really necessary, but what I've done here is I have worked out the rough jump in ionization energy, or the rough difference in IE, as I change from the 7th IE to the 8th IE, 9th IE to 10th IE. What is the difference, or what is the increase in ionization energy? And of course, what we want to look out for is a very big increase in IE, because that will correspond to a change in the principal quantum shell. So for W, 7th and 8th IE, the difference is about 9,000. Again, a rough calculation will do, because we are looking out for significant change, so we can just roughly estimate it. IE number 8 and IE number 9, the difference is about 3,000. Then IE number 9, IE number 10, the difference is about 3,000. So actually this 9,000 difference is significantly larger than the rest of them. So maybe what we can do is we can look at the rest of the elements. And you notice, involving our element X, the difference between 7th and the 8th IE is only about 2,000. Then between 8th and 9th IE, this one increased to 10,000. So this guy is significantly large. And from there we can tell that this will also represent a change in the principal quantum shell. It is actually pretty reasonable because my element W and element X, they are consecutive element. So if there's a big jump in IE from the 7th to the 8th IE for W, then we would expect for the next element X, the big jump in IE will be from the 8th to the 9th IE, and we will expect for Y, the big jump in ionization energy will be from the 9th to the 10th IE. Because they're consecutive elements, so we would expect the big jump in the ionization energy will be in the next ionization energy for the next element. And you notice involving Y, this is also the same. Between IE number 7 and IE number 8, the jump is about 3,000. IE number 8, IE number 9, the difference is about 2,000. IE number 9 to IE number 10, the increase is about 12,000. So this is again significantly large. So this will represent a change in the principal quantum shell. So in this case, we can actually try to deduce the group for W, X and Y. But what I've done here is I've chosen to use W And since we say that there is a big jump in ionization energy from electron number 7 to electron number 8, so what is the meaning of it? The explanation is here. So how do I quantify the 8th ionization energy? Now, removing electron number 8, I'm actually basically having W7 plus. I've already lost 7 electrons prior to this, and I'm trying to remove electron number 8. So this equation will represent the 8th ionization energy for W. And you notice this 8th IE is significantly larger than the 7th IE. So what does it mean? Why is it significantly harder for me to remove electron number 8? It is because electron number 8, it is from a filled inner shell. So all these electrons from electron number 8 onwards, all these will be your inner shell electrons, and all the electrons to the left-hand side will be your valence electrons. So this means that electron number 8 is from a filled inner shell, and so all the electrons prior to that will be in the next principal quantum shell. So I will have 7 valence electrons, and this means that W will be from group 17. So if I look at X, the idea is the same. If I look at X, if I consider a big difference in ionization energy between the 8th IE and the 9th IE, so electron number 9 for X is significantly harder to remove than electron number 8. So why is electron number 9 significantly harder to remove? Is because electron number 9 is from a filled inner shell. So therefore, electron number 8 and before that, all these are considered valence electrons. It is in the next principal quantum shell, and X will have 8 valence electrons, and therefore X will be in group 18. So again, because W, X, Y, and Z, they are consecutive elements, if I can deduce that W, it is in group 17, X must be in group 18, and so on. So all we need to do is we just need to identify the group for one of these elements, and we can figure out the groups for the rest of them since they are consecutive elements. So what we have done is we have determined W, it is from group 17. So now what we can do is we can deduce the groups for the rest of the species. W is from group 17. So naturally X will be group 18, noble gas. Then Y will be in group 1, Z will be in group 2. So deducing the groups for W, X, Y, and Z, once we determine what group W is from, is actually very, very easy. Now finally, coming back to the question asked me to determine which element has the highest first ionization energy. So involving group 17, group 18, group 1, group 2, how do I determine which of these guys have the highest ionization energy? Now, we have learned across the period, the general trend is the ionization energy will increase, correct? Because across the period, the proton number increases, and I'm adding electrons to the same principal quantum shell. So the distance from the nucleus is roughly the same. The electrons do not shield each other, so the shielding effect is roughly the same. So across the period, effective nuclear charge increase, stronger attraction on the valence electron. The electrons will be harder to remove. We will expect between W and X, X will have a higher ionization energy because X is a noble gas. It is on the extreme right hand side. So it should have the highest effective nuclear charge, and therefore it has the highest ionization energy. Now how about X to Y? Now remember X to Y, Y is in group 1, and this electron is actually in the next principal quantum shell. And therefore this electron is much, much further away from the nucleus, and the shielding effect will increase, and the distance from the nucleus will increase. So comparing the ionization energy for X and Y, it is equivalent to comparing ionization energy down the group, because I am removing electron from the next shell, which is much further away from the nucleus, and attraction is significantly weaker, the ENC decreases, and it is much, much easier for me to remove this electron. So I would expect from X to Y, there will be a very, very sharp drop in ionization energy. In comparing X and Z, X should also have a higher ionization energy because involving X, I'm removing electron from an inner shell. Involving Z, I'm removing electron in the next principal quantum shell. So if I compare in this way, then we should know that X should have the biggest first ionization energy. So the answer to this question, of course, will be option B. Alright, so that was the discussion involving question 4. If you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.